problem that I'm going to think about is one in which I know the velocity as a function of time for an Olympic sprinter who's running a 100-meter dash. And the model is going to give me this equation right here. And the goal is for me to figure out what the sprinter's maximum acceleration is. There are actually lots of questions that you can imagine asking about a situation like this, such as given the amount of time, how far have you gone? Or given the distance, how much time does it take? So lots of different questions you can ask here. I'm interested in asking, what is the biggest acceleration that I experience? So I'm going to follow all of the steps here. So starting with understand the problem. The thing that I need to do is know what quantities I've got. So I'm going to go ahead and look at my expression here and see that it looks like there are a couple of important quantities. One of them is C and the other is B. And it looks to me, just from looking at the structure of this equation, that C is going to be some sort of velocity because I've got units of velocity out here. And B is going to be a time because I know that the units in the exponent need to be 1, need to be no units up there. So the fact that T has units of time means that B is also going to be units of time. And the book that I got the problem out of has some possible numbers for these, which I'm going to go ahead and use for this problem. So C is going to be approximately 11.8 meters per second. And the B quantity is going to be 1.45 seconds. And of course, the quantity I'm looking for here is A, or maybe A max, the maximum acceleration. So those are the major quantities that I am interested in. The next thing here is that I want to identify any assumptions that I have made or simplifications for the situation. Here, I'm going to be treating the runner like a point particle, so I'm clearly using the particle model. I'm also assuming that the runner is moving in one direction. Here, that would be the X direction. Those are pretty much the only assumptions that I think I'm making, aside from the form of the equation itself. Last, I'm going to represent what's going on physically, and in particular, I really want to know what this equation looks like, so I'm going to think about graphing it. So if I were to make a quick graph of the velocity versus time, I can do a couple of test points here. First of all, I see that the velocity at t equals 0 is going to be 1 minus e to the 0, which is 1 minus 1, which is 0. So I'm starting down here. And then the velocity is going to change in time. And as this exponent, as the exponent, the e to the something gets bigger, I'm going to get e to the minus that. Right. So as time increases, I have a smaller and smaller e to the minus something. So this velocity as a whole is going to get bigger. I mean, you can always throw this into a graphing calculator if you want, but you end up getting a shape to this graph that looks something like this. So that would be the general shape of the graph. And one thing that I think is really valuable about drawing a motion graph here is that I can right away see from this graph that the acceleration, which is the slope of the graph, is very large at the start, and then is getting smaller and smaller as we go farther in time. And this sort of checks out with my everyday understanding of what it's like to run. I start from rest with no velocity, and then I have some big acceleration at the start, and then that acceleration tapers off once I get up to some known speed. So right away, in fact, I'm going to add this to my problems here. I'm going to go ahead and say that t max, the time at which the acceleration is maximal, is going to be 0. All right, now I have finished stage 1. I'm going to go ahead and save the numbers that I wrote down. I think I can probably get rid of the equation here. So I'll erase that. and then we'll move into thinking about the second part of the problem, which is to actually calculate the unknown quantity. Here, that unknown quantity is the acceleration or the maximum acceleration. So the first thing that I need to do is identify any relevant concepts, laws, or definitions. I think the thing that makes the most sense here is the definition of acceleration, which says that a as a function of time should be the derivative, and this is ax since I'm in one dimension, should be the derivative of the velocity with respect to time. And that's really all I'm going to use here. Given that, I can move on to part 2b, which says to actually solve for it. So I'll go ahead and do that. I have erased the equation, so give me a moment here. I'll flash this back over there. So the equation was c times 1 minus e to the minus t over b. The 1, the first part in the parentheses, is a constant. So when I take its derivative, I'm going to get 0. And then for the rest, I'm going to get a chain rule. So e to the minus t over b is going to give me a minus 1 over b out front. And then I just get the exponent back again. So that's going to knock out the minus sign. And it looks like what I'm going to get here is c over b, c divided by b, times e to the minus t over b. So there is my acceleration as a function of time. And then the last thing I need to do here is actually plug in the time of interest. So that would be ax of t equals 0, which e to the 0 is 1, so it's pretty friendly. So I'm going to get c divided by b. You'll notice here that I was able to solve that totally symbolically. I didn't have to plug in any of the numbers that I know. But I can do that now for part 2c. So I plug in these numbers, and I'm going to get c divided by b. I'm going to do this a little roughly, so I don't have to get out a calculator. So I have 11.8 meters per second divided by 1.45 seconds. So let's see. Let's treat that as about 1.5 seconds, and I'll make this about 12 just to get an approximate answer for us together. Obviously, you can plug these into your calculator and get a little bit more of a precise answer. So I happen to know that 12 over 3 would be 4, and 1.5 is half of 3. So I should get 6 here, or sorry, 8 here for the answer, for the numerical answer. And then the unit should be meters per second divided by seconds, which is going to be meters per second squared. So I get 8 meters per second squared. And again, this is approximate, so I'll put a little approximate here. All right, so now I have an answer. So I'm going to move on to stage 3 here, which is to make sense of this. In making sense of this, I'll start by checking to make sure the units are what I expect. I always want to do this with my symbolic answer. So c over b, and then I'll check up here to see what my units are. And indeed, just like I got when I worked out the numbers, meters per second divided by seconds is meters per second squared. And then check to make sure that that's what I want, which it is, because I want an acceleration, which is defined in meters per second squared. I can also check numbers here. So I want to compare my answer to other numbers that exist in the everyday world. And here I note that I got 8 meters per second squared. And right away, I know a good number to compare this to is g, the acceleration that you get due to gravity, which is 10 meters per second squared. And I think it sort of makes sense to me that this acceleration should be close to g, or at least sort of in the same ballpark. It would be really wild if I got something like 100 meters per second squared, something substantially bigger than g. You could also take a moment here to look up what the top acceleration for sprinters are. When I did that, I got about 4 to 6 meters per second squared. So this might be a little bit on the high side, which may be a flaw in the assumption that we made or the model equation that we used here. Lastly, I want to use symbolic sense making to try to make sense of my symbolic answer, which is right here, that the acceleration should be c divided by b. And for that, I really have to think about what those c and b quantities were, right? Those came from my model. They were part of the equation that I used to model what's going on here. So I have to be really careful about thinking about how I'm going to make sense of this symbolically. I think a good way to do that is to think about what kind of quantity each thing is. To do that, I could think about the graph that I had, which told me something about the velocity. The c that we have here, the 11.8 meters per second, is actually the maximum velocity, which you can see if you go make that graph numerically with a graphing calculator. Which means if I think about how that might impact this, if my runner is going to reach a higher maximum velocity, they're going to need to have more acceleration. And so it makes sense that this c is in the numerator of my expression, right? That a bigger c, a bigger maximum velocity, requires me to have a bigger acceleration. On the other hand, this b quantity is a time-like quantity, and in fact is telling me something about how long it takes for the runner to get up to that top speed. Given that, I could think about, well, if b were larger, if it were going to take me more time to get up to a top speed, I wouldn't have to accelerate as fast at any particular moment, including at the start. So a bigger b might give me a smaller acceleration. And that is, in fact, what happens in this equation. B is in the denominator, so a bigger b ends up giving me a smaller acceleration. And that's using our covariational reasoning sense-making strategy. There might be other strategies that you want to try, but I think that's a good set for this particular problem.